Hello everybody and welcome back to our multimedia networking and architecture for the game networks and fundamentals of game networks classes. Last week we briefly talked a little bit about the history of networking and how different kinds of networking came to be. We looked at some hardware and software specifications. And in last week's class, in the last unit's class, I closed with giving you an overview of the OSI architecture. It's basically a 7-layer architecture that breaks down any network communication between 7 layers: the application layer, presentation layer, session layer, transport layer, network layer, data link layer, and the physical layer. And we talked about the top 4 layers being peer-to-peer layers, in that you on those layers you don't really get into the low levels of communication that require any specific routing data and traffic control. So that's why multiple different devices of different kind, both in terms of the hardware as well as the software platform, can communicate with each other as a peer-to-peer. Those layers were the application layer, presentation, session, and transport layer. Then also last week I talked about the network, data link, and physical layers. Those are the layers that are more involved with the actual communication that happens in the network. And so they require things such as IP addresses, routing information, and all sorts of things. In this unit, we'll start talking a little bit more in detail about each of these communication layers and how they're handled within a network. So within this week, we will start with the physical layer, and we'll talk about physical layer, and then we move forward.
So let's see what physical layer is about. Physical layer essentially is concerned with transmitting and receiving unconstructed bit streams. So as far as the physical layer is concerned, it doesn't care where the information is going, where the information came from, or what is the content of that information. It essentially transmits just zeros and ones, regardless of what those zeros and ones actually mean. It basically defines the electromechanical properties, or the electrical and mechanical properties, of your physical interfaces. It includes connector shapes and specifications and any number of different criteria that you might have. For example, if you look at this picture in the middle, it's a picture of an RS-232 connector, which is essentially a serial cable or a serial connection. And the one underneath it, the blue connector, is called an X21 cable. These are actually the physical criteria and physical properties and mechanical properties of your physical layer. The layer on top of the physical layer is called the data link layer. It ensures uniform transmission of your data by establishing, maintaining, and terminating a link between the two ends of this communication. There are 2 sublayers to the data link layer: the medium access control, or MAC, which regulates the control of the access to physical medium, and the logical link control, LLC, which provides the flow control of this information. And also it's responsible for the detection and correction of lost or erroneous packets that have been transmitted. Examples of data link, or rather logical link control, are Ethernet, which is essentially that LAN cable that we are all familiar with, token ring, high-level data link control, or HDLC, and synchronous data link control, or SDLC. These are essentially mechanisms by which a network is architectured, and the data, or essentially the flow of the data, is being controlled by these mechanisms over different networks.
Alright, the network layer, basically, or the layer that's just on top of your data link and physical layers, is the layer that provides the upper layers the independence from switching technology used to communicate your data. This layer basically is responsible for routing your data from one end to the other end through a network. And this network could be a wireless network or a wired network or any mechanism that you have. And um, and the technology at this point can be either packet switching or circuit switching technology that we talked about earlier last week. This layer also provides services for your internetworking, error handling, and traffic congestion controls. And we will basically talk about the traffic congestion and error handlings a little bit later. The network layer, for example, could include your IP or Internet Protocol or X.24 protocols. Above your networking layer, you have the transport layer. The transport layer is responsible for reliable and transparent transfer of your data between the two endpoints of your network. It also supports services for the end-to-end flow control and end-to-end recovery of the errors in your network. For looking at the examples about transport layer mechanisms, you can talk about the TCP and the UDP layers. And we will talk about both of these or protocols, and we will talk about both of these protocols a little bit later, and you see what essentially makes this different. In a nutshell, TCP is a connection-oriented protocol and requires handshaking, which ensures that your data is going to be transmitted and received with the same order. UDP is a simpler message-based connectionless protocol, which means that there is no need for having an actual dedicated connection between the two endpoints of your networking technology, and it doesn't set up a dedicated line so that in the order of your data transmissions may not be basically guaranteed. You have the session layer and the presentation layer on top of your transport layer. The session layer provides a means for establishing, managing, and terminating connections between processes. So for example, if you have a long file transfer between two hosts, then this layer is in charge of making sure that the connection is established, and whenever the bandwidth is fluctuating, it will take care of that process as well. At this point, you may also resolve the or provide some sort of synchronization and checkpoints to restart a service if connection is seized. The presentation layer performs data transformations to provide a standardized interface to your high-level application. For example, it helps resolve the syntactic differences between the machines that you are dealing with. So for example, if your content is or if your server is a Windows-based server, but your content or clients are essentially non-Windows clients, or even if they're Windows clients, they're using different applications to perform and to look at these these contents. So for example, you may have a Mac, you may have a PC, or you may have a smartphone as endpoints of your network, and so you want to make sure, and this layer makes sure that whatever higher level application you have, the data representation will be taken care of so that your it can be sent and received through your network architecture. And finally, we have the application layer. The application layer is the highest layer in this OSI architecture. It can be used by your user applications, for example, Telnet, FTP, HTTP, SMTP, or MIME, M-I-M-E. And this layer is basically in charge of making sure that whatever data and connection you have on the highest level to the user, they can use their programs to deal with it. So, as we said earlier, the first three layers in this architecture are basically peer-to-peer communication setup layers, and the top level nodes open, set up, and maintain connections for transporting the data, and the actual transporting, routing, and overall management of the data delivery will be taken care of by the last three layers: data link layer, transport layer and network layer. So if you look at this picture, it basically shows you what essentially these layers are made of, or the data that they send. How does it look like? The application layer is maintaining the data. It sends the data down to the presentation layer, and the presentation layer makes sure that it's going to be represented according to the devices that will be using this. It passes that data to the session layer, and the session layer basically maintains and provides a means for establishing connections and managing that. When it's passed down to the transport layer would attach to your data a TCP header, or a transfer control protocol header, which maintains the information that transport layer requires at the other end to be able to resolve any issues or any specific needs that are required. Then the TCP layer sends this packet, which includes the TCP header, down to the network layer. The network layer attaches to the system an IP address or an IP header to your transport data, and basically that is in effect to show where this packet is going to go and how it's going to be delivered to the other end of the system. And then that will be sent to the network data is going to be sent down to the data link layer, and the data link layer creates the Ethernet frame trailer and Ethernet frame headers, which then essentially will be passed down to the physical layer. And the physical layer is basically maintains and sends and receives the 0 and 1s, basically, or the bits and bytes, to the other ends of your communication. To the right, I have essentially another representation, or what we call each of those primary contents of the data in the OSI model. The data is basically whatever you have as the data when it's at the application layer. And then down to the presentation layer, you're basically, that layer is in charge of representing your data, and also if there are any needs to be encryption. And then when it goes down to your session layer, the session layer basically takes care of the inter-host communications, and your data still is in the form of the data that you have. When you pass that information down to the transport layer, which basically sets up the end-to-end connections and takes care of the reliability of your network, the data at that point is going to be called the segments, because each segment then will have attached to it a TCP header. And when that segment is broken down and sent down to the network layer, it's going to be broken down to packets. And that's basically at that level. Here we are now working with packet switching technology. And then the packets essentially would determine where the location of the host and the receiver are, and how this data would need to be routed. And that's the process or the responsibility of the network layer. Then when this data is sent down to the data link layer, the MAC and the LLC, which basically take care of physical representation of your data and addressing of your data, at that point the data bits are going to be called, or the data chunks are going to be called frames. And when you send that down to the physical layer, basically that takes care of media, signal, and binary transmission of your data. At that point you're dealing with bits. Networks set up for communications can be divided into basically two categories based on the distribution over a geographical area. You can have local area networks and wide area networks, LANs or WANs. You can think of the internet as numerous LANs that are interconnected by larger WANs. Although the ultimate purpose is the same, to communicate the information packets, they generally involve different kinds of technologies, different data management styles, and different lower-level medium access control protocols for communications. Local area network, or LAN, is a term that is used for a network when it is restricted to a small geographical area and has a small number of stations. Although there is no upper bound on the number of computers or on the size of the geographical area, there is just one common feature that defines a LAN as a single shared medium to transport data between computers. The protocols to access, use, and relinquish control of the medium are the primary importance in any LAN because it's basically set up to maintain a local presence of your networking technology. These protocols typically reside in your medium access control layer or sub-layer of your data link layer in the OSI specific architecture. The data link layer is logically divided into the two sub-layers that we talked earlier, the medium access control and the logical link control. The MAC, or the medium access control, is the lower sub-layer and is responsible for assembling frames of data at the source and disassembling them at the destination. It performs error correction and node addressing and regulates access to the physical medium using a variety of protocols. Logical link control, or LLC, is a higher sublayer and it performs error control, flow control, and also interfaces with the higher OSI layers. The task for this layer is also to perform addressing for the MAC layer. The MAC layer basically connects a node to the physical medium and governs access to it. A variety of protocols exist which are incorporated into standards that control access to the physical medium and can be divided into some subcategories. We observe three of them: the round robin, the reservation, and the contention. Let's talk about round robin MAC or medium access control category. When you have a shared network and it's organized in a logical ring topology and each of the computers or nodes are connected to the ring, you have to give it an opportunity to transmit in a sequential manner, and that is determined by the logical ring structure. If a node takes over the network to transmit to another receiver on the network, it must let all the other nodes know if it has the control of the network and when it has the control of the network, and then when it transmits its data, and then it can release the network control to other nodes to access it. The access to the network is now open, and the next node in the logical sequence is given the opportunity to transmit its data. The control of handling out terms in the ring structure and can be centralized or distributed. The IEEE 802.5 token ring protocol is an example that can adopt this round-robin strategy to share the network. The picture here shows an illustration for the round-robin technology in 802.5 token ring protocol. In a token ring, token is a special bit pattern and is used to control access. The token circulates around whenever no communication is occurring. So when the network is free, this token basically moves from one place to the next. When a node needs to transmit data, it captures the token, and when it has the possession of the token, it changes the network state from idle to busy and temporarily prevents all other nodes from transmitting any data. When transmission is completed, then the node releases the token and permits other nodes to seize the control of the token. Implementation of this token protocol requires that each node be able to listen where a node is looking for a token if the token is available. And if the token is not available, basically, it waits. When it has the control of the token, then it simply forwards the data, which is basically the token itself. And when essentially the network is in state of transmission, a token will be detected by a node. The node will seize the control of the token, therefore disabling all the other nodes to be able to transmit data, and then it will be able to transmit its own data. The token bit, the token ring can support data rates at 4 megabits per second or 16 megabits per second over shielded twisted pairs of wires. Larger data rates are also possible with fiber optic cables. However, because of their relatively fast transmission, the source node absorbs the token. To resolve this, the fiber distribution data interface, capable of 100 megabits per second, was designed as a successor to the original token ring. It supports dual ring topology, with a primary ring for data transmission and a secondary ring for fault tolerance. The FDDI supports both synchronous and asynchronous methods. So just one more time to go over the example. In the picture here, you have 6 nodes that are connected in the form of a ring. In the upper left corner, or the upper left image, a free token is being just transmitted in the ring topology, and nobody is basically having the control of the ring, and therefore the network is in the idle state. Then in the upper right corner, a free token basically is being grabbed by node B, because node B wants to send the data. Once the node B has the control of the token, no other node will be able to send the data. Node B starts sending its data to node F, and so while that sending process is taking place, node B still has the control of the token. And that's shown in the lower left image here. And once the node B is done transmitting its data, it basically releases the token. So now the token is free to transmit over the network, and the data is being also transferred or transmitted ahead of the token in the network. And so at any given point, when another node needs to capture the token to send the data, they would do so if the token is still available. However, notice if immediately after node B has been done sending its data, if node A needs to send some data, it has to wait until the token goes through the network and reaches its node A, and then node A can basically perform this task. Another approach to sharing a medium is to assign an explicit reservation scheme or an on-demand reservation scheme, where the time on the medium is shared by dividing it into slots, also known as time division multiplexing, or TDMC. In an explicit scheme, each node is assigned reserved time slots to transmit the data. Time slots can be also reserved on an on-demand basis for extended or indefinite time periods. A node that has been allocated a particular time slot is allowed to transmit its data during that allotted time only, and not any other time slot. Therefore, a central control is needed to manage time slot allotment or assignments to prevent multiple nodes from transmitting at the same time. Shared satellite channel is an example of this scheme. An example of time-based reservation scheme is illustrated in this figure. So time 1 is reserved by resource 1 at the first part of this mechanism, and the time 2 is reserved for resource 2, and time 3 is reserved for resource 3. So while computer 1 at the top here has more than the amount of information that it can send into its own time allocated slot, it would have to send whatever it can while its time allocated time slot is available. And when the allocated time changes to the reserved area for node 2, which is the second node down here, then node 1 stops sending the data, gives the network to node 2 and to node 3, and waits until its allocated time arrives, and then it resumes sending the data. That's shown at the bottom of this picture here. Contention. Contention is the third category, or the third mechanism by which we can actually ensure the access in the medium access control layer. Unlike previously discussed, which impose a control to access the medium, in the contention method, we basically impose no control. Every node connected to the medium is allowed to transmit if it finds that the medium is free for transmission. Here, the node that wants to transmit the data must listen to the network to sense whether there is a node that wants to transmit data or not. basically to see if whether data is flowing or not. Also, it's called as a carrier sensing. If there's no data flowing in a network, the node is free to transmit it. If there is data flowing, the node cannot transmit and should wait until a random amount of time before sensing the medium again and check whether it's free for transmission. If it's not free, it has to wait a random amount of time and then sense. And if the medium is free and the data is not flowing over the medium, then the node can send the data. This mechanism lacks basically centralization and decentralization administration and can have multiple nodes transmit data at the same amount of time. So the issue that this mechanism has is basically what we call a collision. Multiple nodes can listen to the medium and see that the medium is free at the same time, and then they think that it's okay to submit the data. When they send the data that is sent by two nodes that were listening to the medium almost at the same time, it will collide, and this is basically called the data collision. So how to resolve collision? To resolve collision, each node also listens to its own transmission and compare it with the original data. If this original data is different than the transmitted data, then there has been a collision, and therefore the node must wait, and if the network medium is free, resend its data. The IEEE 02.3 Ethernet is an example of this method, or contention method, which uses carrier sense multiple access collision detection, or CSMACD. Alright, now that we talked about the local area networks, let's talk about wide area networks. Wide area networks essentially cover wider geographical areas, and they connect various LANs or local area networks together so that the computer nodes on one LAN, which are normally limited to a room or a building, or maybe, for example, like a university campus, can communicate with computers on other nodes located in other local area networks. Probably the most well-known LAN is the internet. So if you're asked what is the internet and what's the difference between the internet and the web, the answer to that question is simply that the internet is the biggest WAN or wide area network that connects all of the local area networks, or all of the Ethernets. And the web is a protocol and a service on the internet. Wide area networks typically are built using routers that connect various public or private leased lines, and often lines or physical mediums that are composed of many different types of wires, fibers, and other lines that provide switching technologies to establish a route. The protocols used to establish connections on such non-shared mediums normally employ switching technologies and use different kinds of protocols, from the broadcast protocols used in medium access layer or MAC layer, for example, that in this case is basically used in local area networks. There are different kinds of switching protocols that we will cover: circuit switching, packet switching, frame relay, and asynchronous transfer mode, or ATM. And of course, the answer to the question to most famous wide area network is the internet. So let's talk about what circuit switching is. In circuit switching, an end-to-end circuit is essentially established in a dedicated manner between the sender and the receiver nodes of your network for the duration of the connection, and also for a specific amount of bandwidth. The public switch telephone network, or PSTN, is an example of a wide area network operating by circuit switching technology. The public switched telephone network initially was put into place for voice communication, but also has been used for data transmission and forms the basis of all modem-based communications, integrated service digital network, or ISDN, and asymmetric digital subscriber lines, or ADSL. So if you think about your DSL connection at home that uses a DSL modem, it's still using a circuit switching technology or public switch telephone network that basically is also used for voice communication as well as data communication. To support multiple users and multiple data rates on the same line, this is often resorts to an instance of time division or frequency division multiplexing. The data rates the circuit switching technology provides are very low and are only sufficient if the demanded data rate by a user is constant. So for example, in data-only transmission, or constant bitrate multimedia video or audio traffic, you can use circuit switching technology. However, if the data rate is variable, especially in real-time multimedia communications, such as the ones that you have on your cable television, circuit switching is generally not sufficient. Packet switching is more efficient for varying data rates and for real-time communications because higher data rates can be accommodated using packet switching technology. Before transmission, the sender node in this technology breaks the data into smaller sections encapsulated into smaller packets. And here's the example, for example, that is shown in this picture. Each packet usually has about 1,000 bytes or less, and with a header that carries necessary information such as the destination address, routing information, and so on. Packet switching technology normally follows one of the two approaches, connectionless and connection-oriented. And it is basically a technology that we will probably get into explaining a little bit later. Packet switching networks provide higher data rates compared with the circuit switching networks. However, the performance starts to deteriorate when network gets congested. So these technologies are essentially vulnerable to congestion. Normally, different arbitration policies basically may be enforced to avoid this situation. Examples of protocols that are implemented for packet switching are X.25, which is the most common, and also the Internet Protocol, or IP, is also another protocol that uses packet switching or is enforced and implemented within packet switching technology. These protocols normally reside on a network layer and also perform extensive error checking to ensure that no data is corrupted during the transmission. The next technology that we'll discuss here is called frame relay. Frame relay is another simple connection-oriented setup that provides capabilities for both switched virtual connections, or SVCs, as well as permanent virtual connections, or PVCs. Modern networks with high bandwidth capacities, such as fiber optics, have lower error rates, making it unnecessary to add an extra bytes per packet for error detection and recovery. These high-speed low-error networks now allow high-speed parts of an established virtual route between two nodes to be time-shared or time-multiplexed for different route connections. Therefore, this increases the efficiency of your network. Frame relay provides a means for statistically multiplexing many logical connections or virtual circuits over a single physical transmission medium. Since many logical connections coexist on a single physical line, each connection needs to be identified with a unique identifier that will allow for the data to be logically tied to a connection. The data link connection identifier, or the DLCI, performs this function. If you look at the figure that is shown in this slide, you can see how this process works. From a user's perspective, frame relay is a multiplex interface to a packet-switched network. Frame relay includes all the operations that are provided by a protocol such as X25, except that there is reduced error checking, which means no acknowledgement, flow control, or error control is required because these mediums have minimal loss or corruption. The error detection, basically, and correction, and flow control can be optionally performed by a higher layer, such as a transport layer. Frame relay is therefore a simplified X.25 protocol with minimal services. Frames of data multiplex can have a length of up to 1600 bytes. Bad frames are discarded, and data rates for frame relay are higher. For example, T1 supports about 1.5 megabits per pixel, and T3 supports up to 44 megabits per pixel. So let's look at this picture and see how it works. When you look at this frame relay example here, you have input ports A through Z, and then when the packets basically come in, the ports are mapped onto different essentially output ports. And so when you're getting your input packets, they go through the ports and they're basically multiplexed out of the output ports. So for example, if you have a dedicated session for a decided route that you have set up, you can basically transmit your packets by multiplexing special kinds of divisions of these packets over the network. Therefore, one line of your input can be multiplexed into several lines of the output, increasing the rates of transmission at this level. The technologies, the switching technologies we discussed before, circuit switching, packet switching, and frame relay, have some characteristics in common. First, they support variable packet sizes, and the transmission can also occur synchronously, especially in circuit switching network, because a dedicated physical or virtual link will be established from sender to receiver. So the packets that are sent by the server will synchronously be delivered to the receiver. In these cases, a connection is established between the two nodes before the data is transmitted and abandoned when the transmission is complete. The two nodes use resources and allocate bandwidth for the entire duration, even when they are not transmitting any data, and even if the connection is set up as a multiplex connection. ATM, or asynchronous transfer mode technology, solves this problem by first statistically multiplexing where packets of all traffic routes are basically merged together into a single queue and transmitted on a first-come, first-served basis, rather than allocating a time slot for all the route when no data is flowing. This essentially tries to ensure maximization of the throughput compared to the synchronous mode transmissions. ATM networks make it feasible to support high bandwidth multimedia requirements in this sense. Another important distinction is that ATM adopts only small fixed-length packets called cells, which provide the additional benefit of reducing latency in ATM networks. As you can see in this picture, in this slide, smaller packets essentially reduce latency during packet switching. But when you basically use an ATM switch network, you create a much better rate of transmission and latency control. So look at the picture above. When you're multiplexing your ATM switches between the multiplex division, when the time is in the picture in the top picture, when the multiplexing is basically trying to get the data from the source, the light gray source coming on top, when it's switched, the entire length of the packet is the time multiplexing between the two packets, and then so therefore the packet 2, when it's trying, or the dark gray packet, when it's trying to be transmitted, it has to wait for the entire T sub 2 time. Whereas if your packets in the ATM switch technology are smaller, then your latency will be smaller, as described in the picture below. The ATM switch, for this reason, can support up to about 2.5 gigabits per second of the data rate. ATM switching also is flexible in working with various technologies such as IP or Internet Protocol, DSL, and wireless, and also is capable of providing guaranteed bandwidth and performance, or called quality of service levels, as we will see a little bit later. Alright, now let's talk about different kinds or different modes of communications that multimedia networks use. And we talk about these because this game network architectures rely heavily on multimedia network architectures as opposed to just general purpose networking. In multimedia communication, or more generally in information communication, we can divide this communication mechanisms into three categories, and we will talk about them: unicast, multicast, and broadcast. Sometimes multicast and broadcast can be considered as equivalent, but we make a distinction because necessarily we want to talk about real-time needs that are needed for broadcast applications uh, in, um, in multimedia technologies. The main difference can be seen between multicast and unicast and broadcast is that at the lower network levels, the routing takes place for the communication of the data, and the way that it takes place, it distinguishes the different kinds of modes of communication. Unicast is derived from broadcast and refers to a setting where one sender node sends information to one receiver node. This can be achieved by setting up a dedicated link between a sender and a receiver. For example, in circuit switching telephony, or in a connectionless links such as sending an email to a specific receiver. Unicast servers work by providing a media stream to each user, an architecture that is hard to scale for many different simultaneous tasks or many different simultaneous users. Multicast is a term used for information delivery to a group of destinations simultaneously over a network. This is more efficient than unicast because it delivers messages to each of the receivers by sending only one copy of the information. The network duplicates the packets only when necessary. Therefore, this conserves bandwidth. Implementing multicast routing is much harder than implementing a unicast routing. In the multicast mode, each multicast receiver can receive information in a unicast manner with one explicit packet sent to each receiver, or in a more sophisticated way where the network resources duplicate packets along different routes toward the end to the receiver. A sender node can also broadcast a message on a network. In this case, the message packet is not intended for a specific receiver node or a set of receiver nodes, but to all nodes on the network if they wish to receive that information. The receivers have to be listening to a broadcast rather than the previous cases where you could specify the delivery of the data to which endpoint or which receiving node it has to be going to. In particular implementations, broadcast protocols use different ports to listen. Broadcasts of live and pre-recorded multimedia data to an unlimited set of receivers over an IP network is a challenging task, especially because all the intra and intermediate synchronizations need to be maintained in the presence of network delay, jitter, and congestion. So basically, probably one of the hardest modes of transmission or communication is the real-time broadcast over an IP network.